Okay, so today we're going to review all of our Chapter 8 concepts. And before we get to that, I want to do just a real quick overview of what we learned with means on the last video. And I want to do that with some multiple choice problems. So after we finish the multiple choice problems, then we'll get into actually reviewing both proportions and means and doing confidence intervals with each. This worksheet I have attached on today's Canvas page. And this is something that we'll go over all four of these problems together in just a few minutes. So this is something that you might want to print out so you have them in front of you. And those can be found on the Canvas page today. Okay, so our first problem here. It says one reason for using a t-distribution instead of a standard normal curve to find critical values when calculating a level C confidence interval for a population mean is that. Okay, so let's talk about the difference between a standard normal curve and a t-distribution. So here's a standard normal curve. Remember, it's got this bell shape. It's centered around the true mean. 68% of the values are within 1 standard deviation, 95 within 2, and 99.7 within 3. So it's this nice standard curve. If you look at a t-distribution, I have a family of curves. Each line is a separate curve. And we have degrees of freedom over here on the side, which is sample size minus 1. So as your sample size increases, my curve here is very wide. In fact, you'll notice the p-value here, the tail probability, 1 standard deviation away from the mean. See how it takes 1 full standard deviation away from the mean to get to the 25th percentile? Okay, so that's pretty short and wide. But as my sample size increases, you can see these values get smaller because it's getting closer together. The larger the sample size gets, the taller and skinnier each of these curves are until it finally approaches the true normal curve, which is what we see down here at the bottom. Okay, so that's the difference. Your t-distribution takes sample size into account. It's wider. It has more tail probabilities than your standard normal curve has. But the main reason we use t instead of z is not only because it allows for us to have some flexibility with sample size, and it's also robust. It can handle a little bit more than z procedures can. And then especially the thing it can handle is you don't have to know the population standard deviation. And so if we look at these choices, z can only be used for large samples. Well, that's not true. We can have smaller sample sizes, and we've talked about that before. Z requires that you know the population standard deviation. That's a big drawback. That's going to be the main problem that we have. That's the main reason we use t instead of z, is because we don't always know that. Z requires that you regard your data as a simple random sample. Well, t does as well. Z requires that the sample size is at most 10% of the population size. Well, t does as well. A z critical value will lead to a wider interval than a t critical value. That's not true. T tends to lead to a wider interval, and we talked about that earlier. Okay, so the big difference is you have to know the population standard deviation in order to use z, and that's the one drawback there, and that's the main reason we use t instead of z. All right, you have a simple random sample of 23 observations from a large population. The distribution of sample values is roughly symmetric with no outliers. What critical value would you use to obtain a 98% confidence interval for the mean of the population? Okay, well, I'm going to use my table to find that, right? And the two things I need to know to find a t-star, a t-value, is I need the confidence level and I need the degrees of freedom. Remember, degrees of freedom is n minus 1, and then the confidence level is whatever confidence level you're told here. So if my sample size is 23, my degrees of freedom is 22, and they told me to use a 98% confidence level. So I'm just going to line those two up on my paper here. So 22 and 98%. And so that's going to give me 2.508 as the t-value that you would use there, the critical value. Remember, whenever they talk about the critical value is the number of standard deviations away from the mean. So that's either z or t. You see that wording on your formula sheet when they give you the confidence interval in words. See right here, it says critical value. That's the number of standard deviations you are away from the mean, either z or t. So anytime you see them talk about critical value, that's what they're referring to. Okay, a quality control inspector will measure the salt content in milligrams in a random sample of bags of potato chips from an hour of production. Which of the following would result in the smallest margin of error in estimating the mean salt content mu? Okay, well first let's talk about what goes into the margin of error. So we know that our confidence interval is your statistic. We're dealing means here, so it's x bar, plus or minus our critical value. Since it's x bar, I'm using t, times the standard error of the mean, which this is what it is for the mean, right? And the margin of error we know is everything after the plus or minus. So what can affect it? Well, the main two things that affect the size of this margin of error is the confidence level, because that's what we use to find t star, right? And sample size. Okay, now notice confidence level. As confidence level gets bigger, it's going to make this number bigger, which is going to make it wider. So confidence level affects it directly. Sample size is in the denominator, so it affects it inversely. The larger your sample size is, the smaller this is going to be, and so the smaller the width. So if I want the smallest margin of error, what I want is the largest confidence level, and at the same time, the smallest confidence level, and at the same time, the largest sample size. If I want the smallest margin of error, I want this to be as small as possible and this to be as large as possible. Okay, so if I'm looking at these, my choices here, well, I know I'm going to go with the smallest level of confidence, right? And the largest sample size, so this is going to be the choice. The reason why I wouldn't pick this is if I had n at 100, but I was doing a confidence level of 99%, that's going to offset each other, right? Okay, so I want the smallest confidence level at the largest sample size. Okay. All right, last one of these. Scientists collect data on the blood cholesterol levels in milligrams per deciliter of blood of a random sample of 24 laboratory rats. A 95% confidence interval for the mean blood cholesterol level is 80.2 to 89.8. Which of the following would cause the most worry about the validity of this interval? Okay, so what I did when I constructed this is I used a t-distribution, right? We would say, okay, the statistic plus or minus the critical value times the standard deviation, right? Now, let's think about the conditions that have to be here. We know we have to have a simple random sample. We know that we can't take more than 10% of the population. And then we know we got to check for normality. Now, my sample here is kind of small. It's not horribly small, but it's a little bit small. So I don't really feel like I could invoke the central limit theorem here. So what I more than likely would have to do, since I'm not told that the parent population is normal, and I'm not told that, I'm not given a large sample, I would have to graph it. And what I would need to look at is, I don't want any skewness and I don't want any outliers, right? I don't want any major skewness. A little skewness is okay, but major skewness or outliers are a no-no. Okay, so what would cause the biggest problem here? The biggest problem would be an outlier. A mild right skew, the t-distribution is a robust distribution and can handle a little bit of skewness. That would be okay. You don't know the population standard deviation? Well, that's fine. That's why we're using t, right? The population distribution is not exactly normal. That's okay too. We can get around that as long as either the sample size is large, or if I graph it and as long as I have no outliers and no major skewness, that would be okay too. So that's not really an issue. And then none of these are a problem. Well, the clear outlier is a problem. Okay, let's do what's called a FRAPI. These are from the book. It just stands for Free Response AP Problem. Yay. Okay, so let's try this. Members at a popular fitness club currently pay $40 per month membership fee. The owner of the club wants to raise the fee to $50, but is concerned that some members will leave the gym if the fee increases. To investigate, the owner plans to survey a random sample of club members and construct a 95% confidence interval for the proportion of all members who would quit if the fee was raised to $50. Part A says, explain the meaning of 95% confidence in the context of the study. All right, do you remember what 95% confidence means? Think back to the very first day when we took notes on Chapter 8. Remember that confidence is not the confidence we have in this specific interval, correct? That 95% confidence is how confident we are in the process used to create this interval. If I were to create many, 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 many intervals using the same process, I would expect about 95% of them to capture the true proportion of all members who would quit if the fee was raised to $50. That's what the meaning of 95% confidence is. All right, part B says, after the owner conducted the survey, he calculated the confidence interval to be 0.18 plus or minus 0.075. Interpret this interval in the context of the study. All they're asking us here to do is to use that other sentence to interpret the interval. That's the conclusion we've been doing, right? So let's figure out what our range is here first. So 0.18 minus 0.075. So our range is from 0.105 to 0.18 plus 0.075, 0.255. Okay, so this is where we would use that sentence. We are blank % confident that the interval from blank to blank captures the true, and then we put it in the context. So let's state that. Ready? We are 95% confident that the interval from 0.105 to 0.255 captures the true proportion of all members who would quit if the fee was raised to $50. We are 95% confident that the interval from 0.105 to 0.255 captures the true proportion of all members who would quit if the fee was raised to $50. All right, part C says, according to the club's accountant, the fee increase will be worthwhile if fewer than 20% of members quit. According to the interval from part B, can the owner be confident that the fee increase will be worthwhile? Explain. Well, does this interval show that the true value is fewer than 20%? No. This interval has some that's fewer, but it's got some that's greater as well, isn't it? So my list of plausible values has some plausible values that are greater than 20%, which would be a problem. So what I would say here is, no, I don't think the fee increase would be worthwhile because there's a possibility that more than 20% are going to quit. Now, if the whole interval had been lower than 20%, then you could say, yes, that's good. But here, since I've got a possibility, remember this is a list of plausible values, I've got a plausible values that are higher than 20%, and that could be an issue. All right, and then the last one of the conditions for calculating the confidence interval in part B is that n times p hat is greater than or equal to 10, and n times 1 minus p hat is greater than or equal to 10. Explain why it's necessary to check this condition. Why do we check this condition? We check this condition to check for normality. Okay, we want to make sure that the sampling distribution can be considered normal-like, and that's why we check that condition. Okay, so what we're going to do right now is we're going to go through that those 4 problems on that worksheet, and it's just 4 confidence intervals. Okay, and so here's what I want you to do. What I'm going to do, I am going to read the problem, talk about it for a second, and then what I'd like you to do is pause the video, try it out on your own, and then unpause the video, and I'm going to have all the answers listed out on a page. Okay, so this is more of a practice and then check yourself type video. Okay, and so I'm going to do that on each one of these. On some of these, I'll walk through step by step, and then others I'll just put the answers down and let you check yourself. Okay. So let's look at this first one. The Forest Service is considering additional restrictions on the number of vehicles allowed to enter Yellowstone National Park. To assess public reaction, the service asked a random sample of 150 visitors if they favor the proposal. Of these, 89 say yes. Give a 99% confidence interval for the proportion of all visitors to Yellowstone who favor the restrictions. And then, after you find that, then are you 99% confident that more than half are in favor? Explain your answer. All right, go ahead and pause this. Try working this out. And then when you're ready, unpause and I'll go over the answer. Okay, hopefully you started with an introduction, which is just a restatement of the question. So I am going to construct a 99% confidence interval to estimate the true proportion of visitors that favor, I don't know what I said there, that favor restrictions on the number of vehicles allowed to enter Yellowstone. Okay, so it's just a restatement of the question. It's a, hey, this is what I'm going to do. I know I'm doing a confidence interval. I know this is the level, and I know this is what I'm trying to find. All right, then we got to check our conditions. Sample has to be a simple random sample. We can't take more than 10% of the population, so we show the population, we show that it worked out, and we show why we checked this. So it's okay to assume independence. Then the last condition, n times p hat and n times 1 minus p hat have to be greater than or equal to 10. Now I need p hat first, right? So remember, you find p hat by saying what you're looking for divided by the sample size. Okay, so you divide that out. So p hat here, I rounded, is about 0.59. And then once that checks out, this is to check to see that we can assume that the sampling distribution is normal-like. All right, then we're ready for actual calculation. Remember, on your formula sheet, you have this in words. In words, it says your confidence interval is your statistic. We're dealing with proportions, so that's p hat, plus or minus critical value. If we're dealing with p's, we're using z as our critical value, times the standard error of the statistic. And your standard error of the statistic, here's proportions, standard error, single sample, here it is right here. Square root of p hat times 1 minus p hat divided by n. Okay, and so you can use your formula sheet to construct this. All right, so p hat was 0.59. Z star. All right, we got a couple of different ways we can find this. Remember, if I'm looking at a 99% confidence interval, I'm going to come down here. I'm looking at the middle 99%, right? That means there's 1% that's split between these two tails. So it's 0.5% here and 0.5% here. So I can do a couple of different things. I can either go to my Z table and I can find 0.005 on here, which it looks like it's between these two. So that's negative 2.57 or 8, okay? Or I could do inverse norm, so second vars, inverse norm, area to the left, so 0.05. Mean is 0, standard deviation is 1. Okay, there it is again. Or what I did is I used what we learned about the t-table, about the t-distribution. Remember how this is a family of curves and each line is a different curve? And as my sample size gets larger, it's approaching the true normal curve, which is this last line. So if I went to 99% here, the number on that last line is Z star for 99%. So 2.576, which is pretty close to what we got on here, as well as what we got on the other chart. So you have 3 different choices here. I think the easiest thing, if you can remember it, is that last line on the t-chart. All right, and then I plugged in p hat, 1 minus p hat, and n. Now, you can either crunch this out by hand, which I did, or you can use the calculator, which I did as well, and got the same answer both ways. So remember, if you're going to use the calculator, you go to Stat, over to Test, and this is a 1 proportion Z interval. You got to scroll all the way down to get to the intervals. 1 proportion Z interval. You're going to plug in X and N. Remember, that's the numerator and denominator of your p hat. No decimals in X and N. Those are counts. So numerator and denominator. Confidence level as a decimal. Then hit calculate. And that's how I got that interval. And then you finish this out with your conclusion statement. I am 99% confident that the interval from 0.49 to 0.69 captures the true proportion of visitors who favor restrictions on the number of vehicles allowed to enter Yellowstone. Okay, good job. All right, let's try another one. All right, the next one says, as part of the final project in AP Statistics, Christina and Rachel randomly selected 18 rolls of a generic brand of toilet paper to measure how well this brand could absorb water. To do this, they poured a 1/4 cup of water onto a hard surface and counted how many squares of toilet paper it took to completely absorb the water. Here are the results from their 18 rolls. Construct and interpret a 99% confidence interval for mu, the true mean of the number of squares of generic toilet paper needed to absorb a 1/4 cup of water. All right, I'm going to start this one out with you because this one's a little different in how we're going to check the conditions. Okay, so we're dealing with means, right? All right. Either way, whether it's means or proportions, I always start out with an introductory statement. So I am going to construct a 99% confidence interval to capture the true mean number of squares of generic toilet paper needed to absorb a 1/4 cup of water. Conditions. Was it a simple random sample? Well, yeah, it said that they selected 18 roles randomly, right? Okay, so I've got to make sure that I didn't select more than 10%. So the population would be all rolls of toilet paper. And I am assuming that there are more than 180 rolls of toilet paper, right? So definitely okay to assume independence. Okay, now, normality. Okay, here is where it's different. Here's why I did this one with you. Okay, to check for normality with means, either the parent population can be normal. Well, they don't tell us that. Or my sample size is large, so the central limit theorem lets me know the sampling distribution will be normal-like. I don't have a large sample here. So what I've got to do is I've got to graph this data and make sure that there are no major outliers here. Okay? Now, skewness, a little bit of skewness is okay. Remember, T is a robust distribution and can handle a little bit of skewness. It can't handle outliers, especially with smaller sample sizes. So here's what we're going to do. We're going to plug these values into a list, and we're going to graph it on our calculator. Okay? So on your calculator, you go to Stat, Edit. If you have anything in your list, highlight the list, hit Clear, and then Enter. Clears it out. And then go ahead and type all 18 values in your list right now. Okay. Make sure I have them all in here. Okay. Once you have everything in your list, do you remember how to graph? It's been a while, right? Okay, so stat plot is where we're going to go to graph. See right above y equals? So you're going to do second y equals. Go into the first plot to hit enter. Hit enter again to turn it on if it's not already on. Go down and select the first histogram. So hit over until you're on the histogram that shows outliers. Hit enter. Make sure your X list says list 1 because that's where we put it. Leave frequency as 1. And when all of this is set up right, you're going to go to zoom and then go down to zoom stat, number 9. Okay, and ignore my line, that's for a different thing. See my box plot here? Does that look pretty good? Yeah. Okay, so I'm going to say graphed box plot of data. No outliers or skew. Okay to assume sampling distribution is normal-like. Okay, and what I might actually do also, especially on the AP exam, is I might kind of sketch what's going on here with this one. You could just kind of draw your picture. If you hit trace, it'll tell you what these values are. That's 20, 23, 25, 27, and 29. And see how that's all nice and evenly spaced apart, so that shows it's nice and symmetrical there. Okay, so that's how you do that. If it doesn't tell you the parent population is normal-like and it's not a large sample size, that's what you're going to do there. All right, let's go ahead and finish this out. So next thing, we're ready for our formula. So statistic, we're dealing with means, so that's x bar. Plus or minus critical value, since we're dealing with means, that's going to be t star, times our standard error with means would be this. So now I need the mean, and I need the standard deviation, right? Okay, so you have your data in a list, correct? If you go to stat edit, it's still there. So I'm going to run 1-bar stats on this list to find the mean and the standard deviation. So stat, calc, 1-bar stats. And if you just tell it on list 1, nothing else, just list 1. If you didn't have StatWise running, just hit enter. Okay, so the mean here is 24.9. Plus or minus, now t star. Got to find our t star here. If n is 18, My degrees of freedom would be 17, right? Okay, and we want to state that somewhere. That's part of our work. Okay, so then if my degrees of freedom is 17 and we're doing a 99% confidence interval, I'm going to go to line 17 on my T-chart, line it up with 99%, and get 2.898, I believe. Times, okay, go back to my calculator for standard deviation. Now you're going to use S of X standard deviation, so 2.86 we'll call it, over the square root of n, which is 18. Okay. Now again, you can crunch this out if you want to by hand and figure out your interval, or on my calculator, I can go to Stat, over to Test. Now since this is means, this is just a T interval. With proportions, you do a 1 proportion Z interval. With means, you do a T interval. Now, on this one, I can type in the values, or since my data's in a list, look, it already pulled up. See how it already pulled up the mean and the standard deviation for my list? It already pulled that. It already pulled everything for me, okay? Or, if it didn't pull it for you, if you go over to Data, hit Enter, tell it, hey, pull everything from list 1, leave frequency at 1, put the confidence level at 99%, calculate. There it is. And look here. Not only does it give you the interval, but it gives you the mean and standard deviation on this page. So I really didn't have to run one of our stats earlier. I could have just run this, and it would give me the values that I need to plug in. Okay? So my interval, and because of the way it's done, I'll probably go ahead and go out all the way. 22.991 to 26.897. Okay? All right. And now we're ready for our conclusion. I'm running out of room here. All right. So I am 99% confident that the interval from 22.991 to 26.897 captures the true mean number of squares of generic toilet paper needed to absorb a 1/4 cup of water. Okay. And I think that's all it wanted us to do, right? Just was the interval. And we're done. Oh, you know what? I keep doing this. I didn't answer the last question on the last one. Okay, so let me give you a second. Make sure you have absorbed all of that. And let's come back up here, because guess what? I didn't answer the final question on this one. Okay, we found the interval for the Yellowstone, right? But we didn't answer the last question. Are you 99% confident that more than half are in favor? So let's go back to this. Are you 99% confident that more than half are in favor? Is that whole interval higher than half, 50%? No, I've got a plausible value that's below 50. So no, I am not 99% confident that more than half are in favor. I've got a possibility that less than half are in favor. More of the interval is higher than not, but there's still a plausible value below 50. Okay? And that one didn't have a second question. All right, let's try 2 more. Okay? All right, so for their second semester project in AP Statistics, Anne and Tori wanted to estimate the average weight of an Oreo cookie to determine if the average weight was less than advertised. They selected a random sample of 36 cookies and found the weight of each cookie in grams. The mean weight was 11.3921 grams with a standard deviation of 0.0817. Okay, I'm going to have you pause the video now and go ahead. On A, you're constructing the interval. And this time, I'm not going to forget. We're going to then answer B based on that interval that you construct after that, okay? So pause the video, and then when you come back, I'll have it fully worked out. We'll go over it real quick and answer the question. Okay, so here's the answer. So hopefully you started with an interval here. Introduction. I am going to construct a 95% confidence interval to estimate the mean weight of an Oreo cookie. Then you wanted to check your conditions. It's a simple random sample. Since it's a simple random sample, we had to check that we didn't take more than 10% of the population of all Oreo cookies, which we definitely didn't. So it's okay to assume independence. Here, the sample size was large, so we could use the central limit theorem as our reason why we know the sampling distribution is normal-like. All right, then we're ready to go ahead and start finding the formula and calculating it out. So statistic plus or minus critical value times the standard error. So mean plus or minus t star times s of x over square root of n. They told us that was the mean. To find t star, now you could have done two different things. Here I used inverse t to find t star. And notice that's what I stated here. Here's my degrees of freedom, but I used the calculator to find t star. If instead you used line 30, because degrees of freedom 35, there was no line 35, right? Just make sure you make a note of it and state what you found. So see how it's a little bit different, but I stated, here's my degrees of freedom, here's what I used, here's what it is. Here's my degrees of freedom, here's what I used, here's what it is. Either one of these is okay, because look, if I crunch this out by hand with the one on the table, or I use my calculator and do the t interval, either way I got the exact same answer, didn't I? Even though the t star was a little bit different, okay? And then hopefully you finish out with a conclusion. I'm 95% confident that the interval from 11.36 to 11.42 grams captures the true mean weight of an Oreo cookie. Okay. All right. So let's go back and answer the last part of this question. It says, on the packaging, the stated serving size is 3 cookies or 34 grams. Does the interval in part A provide convincing evidence that the average weight of an Oreo cookie is less than advertised? Okay, well, it's advertised that if 3 cookies are 34 grams, that means on average, each cookie should be 11.33. Well, look at our interval. Well, actually, what we found was they weighed more than advertised, didn't we? The whole interval is more than what the claim is. So actually, on the contrary, I think I have evidence that they're actually way more than what's being advertised here. All right, last one. Miss Quinn's class took a simple random sample of 102 pennies and discovered that 57 of the pennies were more than 10 years old. Calculate and interpret a 99% confidence interval for the true proportion of pennies from the collection that are more than 10 years old. Is it plausible that exactly 60% of all the pennies in the collection are more than 10 years old? Explain. Okay, so A is just running the full confidence interval, and then once you have the confidence interval, you can answer B. So again, pause the video. Try this on your own, and when you open it back up, I'll have the answers all out for you. Okay, let's check your work. So hopefully you started out with an introduction. I'm going to construct a 99% confidence interval to estimate the true proportion of pennies from the collection that are more than 10 years old. Then check conditions. So we got to make sure it's a simple random sample, which it was. Then we need to make sure that we didn't select more than 10% of the population. And I'm hoping there were more than 1,020 pennies in this collection. And so I think it's okay to assume independence here. And then to check for normality, remember you want to show formula, you want to show plugin, and you want to show why you're checking it. So n times p hat, n times 1 minus p hat, both have to be greater than or equal to 10. When I show those calculations, they are, so it's okay to assume that the sampling distribution is normal-like. Now, all of that is so monotonous, but that is the most important thing that you're doing. That's one of the things that the graders are going to look for on the AP exam. So make sure you are very thorough with your conditions. All right, then we're ready for the actual calculation. So we're going to show our formula. Statistic plus or minus critical value times standard error. So statistic is p hat since we're dealing with proportions. Since we're dealing with proportions, our critical value is z. And then here's the formula for the standard error. Show plugin, again, finding z, the easiest way is if you go to your t table, but use the last line because these are the z's, right? Right above 99%. Or you could use one of the other two ways. Show plugin. And then you can either crunch this out or you can go to your calculator. Go to stat, test. This is a 1 proportion z interval. And make sure you go down to the intervals. Remember, if it's means, you use the t interval. If it's proportions, you're using the 1 proportion z interval. You're going to type in your x and your n for your p hat, so 57 and 102, and the confidence level. Calculate, and then there's your interval. And then state your conclusion. I am 99% confident that the interval from 0.43 to 0.69 captures the true proportion of pennies that are more than 10 years old. Okay. Now the last part of this question says, is it plausible that exactly 60% of the pennies in the collection are more than 10 years old? Is that plausible based on our interval? Well, sure, because 60% is in the interval, isn't it? So it is, yes, a plausible value because it's within the 99% confidence interval that we created. So yeah, definitely plausible here. Okay, now that's it for that worksheet, but what I want to do is finish out with just 2 problems estimating sample size. Okay, so these are not in that packet, but I do want to go back over this because it's been a little while since we did this, and we only did one at the end of the last lesson. Okay, so on this one it says, suppose that you want to estimate P, the true proportion of students in your school that have a tattoo with 95% confidence and a margin of error of no more than 0.1. Determine how many students should be surveyed to estimate P within 0.1 with 95% confidence. Okay, so what are they asking us to find here? They're asking us to find how many students. That's N, right? I need a sample size. They're telling us this is what we want the margin of error to be no more than. Okay, so what does the margin of error equal if we're dealing with proportions? Okay, well, on our formula sheet, remember the margin of error is everything after the plus or minus. And if I'm dealing with proportions, I've got a critical value, that would be z with proportions, right? And then the standard error would be the square root of p hat times 1 minus p hat over n. So margin of error would be z, and then p hat times 1 minus p hat over n. Okay? Now, I want the margin of error to be no more than this, right? I want this to be this much or less. Okay? So I want it to be, the margin of error to be, when I calculate this, I want it to be that much or less. Okay? And you can just do equal sign for right now and then think about that at the end. All right, so they told us the margin of error is no more than 0.1. My pen's not working. Z star, well, I got 95%. So if I go to my table, down here, remember last line is Z, so 1.96. Now, what do I do about p hat? Do you remember what we do? If we don't know p hat and we're trying to solve for n, remember you are going to use an estimated 0.5, right? Because that's where my margin of error would be the largest. I'm just erring on the side of caution, so 1 minus 0.5 is also 0.5. And now I just have a little algebra to do. Okay? So on my calculator, I'm going to say 0.1 divided by 1.96. Whoops. Okay, so I moved that over, right? Then I can square both sides to get rid of that square root. Okay. If I multiply, so at this point I have said, okay, 0.1 divided by 1.96, and then I squared it. And so what I'm left with is now 0.5 times 0.5, which is 0.25 over n, right? So I need to multiply n to the other side. And then I need to say 0.25 divided by all of this. So I could say 0.25 divided by, you remember your second answer button? See, it's right above the negative sign. If you do second answer, it pulls all that back up so you don't have to type it in. Okay, and so I get n is 96.04. So I need my sample size to be at least 97. Remember, you'd rather have a too large sample than a too small. Okay. Now let's try one of these with means. So you want to estimate the mean fuel efficiency of Ford Focus automobiles with 99% confidence and a margin of error of no more than 1 mile per gallon. Preliminary data suggests that the population standard deviation is 2.4 miles per gallon. It is a reasonable estimate of the standard deviation for all cars of this make and model. How large a sample do you need? So again, I need to know what the margin of error is. And remember, the margin of error is everything after the plus or minus in your calculation. So it's your critical value. Okay, well, normally when I'm dealing with means, I would use T, right? But they give me a population standard deviation estimate. Plus, remember, we can't use T if we don't know the sample size. So my margin of error, I'm going to use Z in this case, times my estimated standard deviation over n, right? So the margin of error is no more than 1. If I'm doing 99% confidence, again, I'm doing Z because I don't know sample size. We can't use T, so 2.576. Standard deviation is 2.4. And then I just need to solve for n. The first thing I might do is multiply that over to the other side, right? So square root of n equals, let's see, 2.576 times 2.4. So that's 6.1824. This calculation is a little easier than the proportions, right? And then square both sides to get rid of that squared. So 38.22. So I need it to be at least 39 cars. Oh, I guess it's miles per gallon. Okay, so I need at least 39 of whatever I'm looking at here. Okay. All right, so that was a good overview of what we've done so far. I would go back, and if there's any of these that you are unsure of, try them again. Try working through them again. Go back in the video and find the solution and look it over and make sure you have that down. And just practice making sure you have all of the steps down. You are now to do the review, and then you can do the practice test for extra credit as well. And let me know if you have any questions at all. If you need me to work through any of these again, or anything on the review or practice test, okay? All right, see you soon.